Hi, this is Mrs. Baisden, and today we're going to talk about atoms, isotopes, and ions. So atoms make up all matter, so they're the smallest identifiable units. When you look at an atom, it has two major parts: the nucleus, which is the core of the atom, and that's where the protons and neutrons are contained, and then the rest of the atom is mostly empty space, but that's still where the larger volume of the atom is contained, and that's the electron cloud. So those electrons are dispersed within that electron cloud. Within the atom, there are three subatomic particles that we're going to talk about: protons, neutrons, and electrons. Protons are found in the nucleus. They have a positive charge, and they have a mass of 1 atomic mass unit. And you can see there, they also have a mass of 1.67262 times 10 to the negative 27 kilograms. The atomic mass unit is a unit that we use that makes it a little easier to describe something that small. So a proton, we would say, has a mass of 1 AMU. Neutrons are also found in the nucleus. They have no charge, or we would say they're neutral, and they also have a mass of 1 AMU. The electrons are found in energy levels in the electron cloud. The electrons have a negative charge, and they have a very, very small mass. So the reason there's a picture of an elephant on this page is that one author once described electrons like fleas on an elephant. So if you have an elephant and you go to get his mass, if the elephant has a couple fleas, it's not going to affect it. Same thing goes for electrons. If you have electrons, their mass is so small that it doesn't affect the mass of the atom. The mass of the atom comes from the mass of the protons and the neutrons. While we're talking about electrons, there's special types of electrons called valence electrons. The valence electrons are the ones that are found in the outermost energy level. These are electrons that are important because these are the ones that can be lost, gained, or shared during chemical reactions. This is a comparison chart that shows all the different particles. So if you look at protons and neutrons, you can see protons have a charge of +1, neutrons have a charge of 0, and their mass is about the same. The electrons have a charge of -1, but their mass is a lot smaller than the mass of the protons and the neutrons. So when you are looking at this as far as what you need to know by the end of the chapter, you don't have to know the specific mass, you just need to know relative masses. So what that means, you need to know that protons and neutrons have about the same mass, and that electrons' mass is very, very small in comparison. You also want to make sure you know the charge. So you know that protons are positive, neutrons are neutral, electrons are negative. When we are looking at a block on the periodic table, there's a couple different numbers that we want to notice. The first number is either above the symbol or it's up in the top corner. The periodic table in our room, it's the small blue number in the upper right corner. This number is called the atomic number. This is the number of protons in the nucleus of an atom. Protons are important because if you change the number of protons, you change the identity of the element. The atomic number is notated with the symbol Z. So if you see Z equals a number, that means that's the atomic number. So for example, this one that's on the screen right now, we would say Z equals 6. That tells me the atomic number. So when I go to the periodic table in the classroom and I look at the blue number, that tells me what the element is. And then that also tells me that there are 6 protons and 6 electrons if it's a neutral atom. So we'll talk through a couple examples of how to do that later, but if you have a neutral atom, the number of protons is the same as the number of electrons. And by neutral, we mean the overall atom does not have a charge. The next thing in a block on the periodic table is the chemical symbol. So these are 1 or 2 letter abbreviations. One of the most important things is when you are writing these, the first letter needs to be a capital letter and the second number needs to be lowercase. Now, if you're someone that writes in all caps, you have to make sure that that second letter is small enough where you can tell, because there can be some confusion if you use 2 capital letters for a symbol of an element. So the chemical symbol is in the middle. Those symbols come from abbreviations of the English word for an element. Some of them come from Latin names, and as we get into the periodic table, we'll talk a little more about where the names of some of those elements come from. But that's why when you look at the periodic table, not all of the symbols for the elements are just the first couple letters of the name that we know is because some of these are abbreviations from Latin names. The final number on a block on the periodic table is the atomic mass. And on our periodic table in the classroom, again, this is the red number that's at the bottom. This is a weighted average of the mass of an atom of the element. So there are, in a second, we're going to talk about isotopes. So there are different versions of the same element. So to find that average atomic mass that's listed, this is the reason it's a decimal, you take a weighted average, and we'll learn how to calculate those later on. So this takes into account the abundance of an element's naturally occurring isotopes. So an isotope is an atom with the same number of protons, so it's the same element, but it has different numbers of neutrons. So it's like different versions of the same element. Isotopes are interesting because you can have an isotope of the same element, but the properties of those isotopes can be very different. So if we look at an example of like carbon-12 versus carbon-14, those are two different isotopes of carbon. One of those isotopes, carbon-14, is radioactive, which is going to give it very different properties. When you're talking about a specific isotope, those are specified or called nuclides. So there's a couple different ways to represent specific isotopes. There's a couple different ways of notating those. So on the top there, you can see one way to notate it would be the chemical symbol would be on the right, the mass number would be at the top, and then the atomic number would be at the bottom. So if we use our example, if we go with our carbon-12 example, this is what this would look like. So we would use the symbol for carbon, C. The mass number, if we're talking about carbon-12, would go on the top, and then the atomic number for carbon would go on the bottom. Now, if we were going to show the other isotope, or one of the other isotopes of carbon, carbon-14, it would look like this. So the bottom numbers are still the same because the atomic number, like we said, is what identifies the element. So we're still talking about carbon, but that top number, because those are isotopes, the mass number is different. Another way to notate an isotope is by using this notation at the bottom. This is a little different. So all it shows us is the chemical symbol or name and the mass number. So if we were going to show carbon-12, we would show it like this, versus carbon-14, which would look like this. So it's important to remember that that dash there, that's not a negative sign, that's just a dash. And all that does is that notates that this particular version of carbon has a mass of 12 compared to this version of carbon, which has a mass of 14. Here's another example. So any sample of an element, or most samples of an element, contain their isotopes. So if you're looking at a neon sign and it's filled with neon, neon has 3 naturally occurring isotopes. So you can see that neon 20, neon 21, and neon 22. So you can see that neon 20 is the most abundant isotope. So most of a sample of neon is composed of neon 20, but you have a little bit of neon 22 and a tiny bit of neon 21. So when you're doing the calculation for the average atomic mass, usually the average atomic mass reflects the most abundant isotope. And we're going to talk about isotopes more in a couple days, but this is just something to kind of keep in the back of your mind. So if you look at the bottom, you can see the notation for those 3 different types of neon. So neon 20, so here's another way to write it, neon 21, and neon 22. And notice at the bottom, all of these on the bottom have 10 because 10 is neon's atomic number that identifies it. So if that bottom number changes, it changes what the element is. The other thing you can look is what the number of protons, neutrons, and the mass number is. So 10 protons, it has the same number of protons because, again, that identifies the element. If this number changes, then I'm no longer talking about neon. Isotopes, by definition, have different numbers of neutrons. So neon 20 has 10 neutrons, neon 21 has 11, neon 22 has 12. And then you can see that their mass number also reflects that. They each have different masses, even though they're the same element. The natural abundances we'll talk about in a couple days when we talk about how to calculate an average atomic mass. Last thing we're going to look at today are ions. So when atoms gain or lose electrons, they become ions. So cations are atoms that have lost electrons and they become positively charged. Anions are atoms that have gained electrons and they become negatively charged. So one way to remember that is that cations has a plus in it So this has a plus sign in it. And then anions, you can think of a negative ion. So cations become positive, anions become negative. Cations, again, they lose electrons because now they have more protons than electrons. Anions gain electrons because now they have more electrons than protons. We notate ions using the symbol for the element from the periodic table with a positive or negative numerical superscript to indicate the charge. So the charge of that ion depends on the number of valence electrons of that substance. So we will talk more about how to figure out what something becomes. So the charge of the ion is not the same as the number of valence electrons, but it depends on whether that atom gains or loses its valence electrons. So in our example here, sodium becomes positively charged, so that means it's lost 1 electron. Strontium gets a +2 charge because it's lost 2 electrons, and then phosphorus becomes a -3 because it's gained 3 electrons. So when we are trying to calculate subatomic particles, there's a couple different ways we can do this, and we'll do lots of practice in class on how to figure this out. So they can be determined using either the periodic table, symbols for specific isotopes, or symbols for ions. So there's lots of different ways that you could get this information. So we're going to do practice with all different types. So the atomic number, if you know the atomic number, then that is equal to protons, which is equal to electrons, as long as the element is neutral. So as long as it doesn't have a charge next to it. To get neutrons, you're going to take the mass number. If it comes from the periodic table, you're going to round it, minus the atomic number. If you have a specific isotope and you want neutrons, you're going to take the mass number for that isotope minus the atomic number. Okay, so again, we're going to do lots of practice with this. So we're going to start today with a couple examples, and then when we come back in class tomorrow, we will go over a lot more examples together. So for this one, it says determine the number of protons, neutrons, and electrons in an atom of the following element. So we are going to figure out protons, neutrons, and electrons for neon. So if all they tell me is neon, then the only place I have to get that information is the periodic table. So I'm going to look at the atomic number, or the number on the top, to get protons. So protons are going to be 10. Since there's no charge on this atom, it's just neon, it's just a neon atom, protons and electrons are going to be the same. To get neutrons, I'm going to use the bottom number. So the bottom number for this is, and when I'm doing it this way, I'm going to round it. So I'm going to take 20, which is the mass, and that's the number that's at the bottom, minus protons. So my neutrons would be 10. Okay, now in this case, you have 10, 10, and 10. You have the 3 numbers the same. Sometimes that happens, sometimes it doesn't. So it's not always going to be the same. Okay, here's another example, and this one is for a specific isotope. So this is for carbon-14. Protons I still can get from the periodic table. So I'm going to look at the atomic number. So the atomic number of carbon is 6. So there are 6 protons. Electrons, this is neutral. There's no charge on it. So electrons are going to be the same. That's also going to be 6. And then for neutrons, since this one gives me a mass, that's what I'm going to use for my mass number. So I'm going to take 14 minus the number of protons. So that means my neutrons for this is going to be 8. So 6 protons, 8 neutrons, 6 electrons. And then the last example we'll do is for an ion. So this is a calcium ion. So again, I'm going to go to the periodic table, and that's going to give me my number of protons, because protons is the same as the atomic number. Since it's not specifying an isotope, I'm going to round the mass number from the periodic table. So I'm going to round that to a whole number, which would be 40, minus my protons, and that gives me neutrons. Now for electrons, I have to do this a little differently because it has a charge on it. So if it's a +2 charge, that means it has 2 less electrons than protons. So it's only going to have 18 electrons. So when you add those protons and neutrons together, that should give you the overall charge. So if I have 20 positive charge and I have 18 negative charge, that gives me a plus 2 charge overall, which is what this number is up here. So basically, if you have a positively charged ion, you're going to subtract that many electrons from the protons. If you have a negatively charged ion, you're going to add that many electrons to the number of protons to get your total number of electrons.